Okay, the recording has started.
Okay, thank you for the introduction and for the invitation to be here today. In this talk, I'll tell you how the period following a neutron star merger lasting for about 3 to 10 seconds is crucial for generating the ejecta that will make the kilonova counterpart to the neutron star merger. And that's a thermal transient that is the easiest to detect because it's pretty much isotropic. Okay? We're thinking here, of course, the LIGO sources, neutron star mergers, and the image you see on the right is, probably everybody knows it, is the sky localization of GW170817. And you see that by looking at the kilonova, you can improve the localization with optical telescopes by a lot more than what you obtain from the gravitational waves or the gamma rays. Okay? And on the left is just a snapshot of a GRMHD simulation of the accretion disk that forms after the merger, and which, at least for the parameters that we infer from GW170817, is said to be the dominant source of ejecta for the kilonova. So the plan of the talk is to give you a very brief review of neutron star mergers, focus on the electromagnetic counterparts. Then I'll talk about the physics of accretion disks and mass ejection. And then I'm going to talk about the dependencies, physical dependencies for the neutron star merger disk in terms of magnetic GRMHD dynamics and neutrino physics and so on. So the broad context here is time domain astronomy, and the motivation for making predictions here is to connect with the transient surveys that are taking place in astronomy, many of them, and also the gravitational wave follow-up of the sources by these transient surveys. And the science questions have to do with the origin of elements, in particular heavy elements, heavier than iron. And then questions related to fundamental physics, such as the equation of state of dense matter, physics in strong gravity or strong magnetic fields, neutrino physics, and then more astrophysical questions, such as the formation of compact objects, what fraction of supernovae are successful or failures, and then other things like the origin of short gamma ray bursts. So neutron stars, I'm sure here everybody knows about them. They are the densest objects in the universe, made of matter, of course. And they're interesting, at least for physicists, because in their central regions, the density exceeds the density of atomic nuclei, which means that we can use them to probe physics at densities higher than what we can reach in the laboratories on Earth. So they're cosmic laboratories for dense matter physics. And the way this usually takes place is by comparing observed masses of neutron stars and hopefully radii are harder than masses, and then comparing that with theoretical models for the structure of the neutron star. What you see on the right here is a mass radius diagram, and the curves are obtained for different equations of state of dense matter, which here are theoretical models. And for instance, if the maximum mass that a given equation of state predicts is lower than the observed maximum mass of a neutron star, which is about 2 solar masses or 2.1 or so, then that equation of state is ruled out. It's kind of science that can be done with neutron star mergers. And then, of course, they were discovered in the 1960s by Jocelyn Bell as radio pulsars. And since then, they have been detected at many other wavelengths, including gamma rays, X-rays, optical, etc. And then, of course, we have the neutron star merger, GW170817, that yielded a short gamma ray burst, the gravitational waves, of course, and the kilonova transient. Now, where do neutron stars come from? They come from massive stars, in particular when they explode as supernova. In stars more massive than about 8 solar masses go through advanced burning stages. And temperatures are higher, so the Coulomb barriers can be more easily exceeded. And at masses more than about 11 solar masses, all the nuclear fusion reactions are exhausted, and the nuclei with the highest nuclear binding energy are reached. That's usually iron and iron group elements. And an iron core develops at the center of the star. Since no more fusion takes place, the only way to support this against gravity is electron degeneracy pressure. And as most of you probably know, structures supported by electron degeneracy pressure have a maximum mass, the Chandrasekhar mass. Here, that maximum mass is modified a little bit by other processes such as photodissociation. But eventually, because right outside the iron core, there's a silicon burning shell that's dumping ashes on it, the iron core grows in mass steadily, and eventually it reaches its maximum mass and collapses. That's what we call the core collapse. And the iron core collapses, but then once the central regions of this iron core exceed nuclear density, the equation of state is such that matter becomes harder to compress. And we say that it stiffens. And what that means is that a dense structure is going to form at the center. We call it a proto-neutron star, and a bounce acoustic wave initially communicates to the rest of the star that collapse has been halted, and then the acoustic wave steepens into a shock. Okay? The shock does not immediately blow up the star because there are heavy energy losses to neutrino emission and nuclear dissociation, and it stalls. And so in the classic delayed neutrino mechanism, what happens is that because the proto-neutron star is so hot and dense, neutrino emission is significant. Yeah, we saw neutrinos from supernova 1987A, so we know that this occurs. Right? And then some of those neutrinos are reabsorbed right inside the shock, and then they deposit just enough energy to blow up the star. Right? And there are complications such as multidimensional effects and turbulence and convection and so on. But the point is that this classic mechanism, at least the latest 3D models show that it does work. Of course, that is isolated stellar evolution. In reality, more than half, at least that's what the observers find, more than half of massive stars are in binaries or in multiple systems. And the binary evolution modifies a bit the evolutionary path of a given star because we can have things like mass transfer and a common envelope. And in the case of a binary system with two massive stars, we have a supernova first of the more massive star, and then the other one continues in the main sequence. If the supernova does not disrupt the binary system, it continues to exist. Eventually, the second star evolves, explodes as a supernova, and if a number of conditions are met, we can end up with a compact object binary. It could be two black holes, it could be two neutron stars, or a neutron star and a black hole. Prior to 2014, a lot of this was mostly theoretical predictions. We knew about double neutron stars in the galaxy. We knew about 20 of them. But we have never observed binary black holes and also neutron star black hole binaries. But of course, as we all know, LIGO detected binary black holes in 2014, and since then it has detected a lot of sources. They've published by now 3 catalogs associated with the 3 observing runs that they've had. And in the latest one, GWTC3, they have 90 sources with probability of being astrophysical more than 50%. And it's mostly binary black hole mergers. Okay? There's a handful of black hole neutron star mergers candidates. None of them show the electromagnetic counterparts. And the 4th observing run is beginning now in May, mid-May, I believe. 20-something of May. And so we will have even more sources because the sensitivity should have improved a bit. And so we have a lot of black hole statistics now, binary black hole statistics and mergers. And so that is allowing people to study questions such as the mass distribution of black holes and what fraction of supernovas succeed and which fail, what is the maximum mass of these black holes, what is the limit to peri-instability supernova, for example. So with large samples, one can start asking more detailed questions about stellar evolution. So this plot here, they always show it in LIGO talks. The x-axis doesn't mean anything. The y-axis is essentially the mass. And basically, this is just a sequence of all the binaries that they have found. So yellow is electromagnetic neutron stars, red is electromagnetic black holes, blue is gravitational wave black holes, and then orange is gravitational wave neutron stars. And you notice it's only a few of them. Okay? Some of them are ambiguous. We don't know if they're neutron stars or black holes, so they have blue, have orange, and sometimes they call them a mass gap object because they are in between the maximum mass of a neutron star and something like 5 solar masses or 6 solar masses, which we think should be the minimum, roughly minimum mass of a black hole that is formed in stellar core collapse. Of course, GW17 was 2 neutron stars, we believe. There have been studies that show that you could possibly get the same kilonova with a black hole and a neutron star, but most people agree that it's just 2 neutron stars, and the end result was a black hole with something like 3 solar masses. So you can produce 3 solar mass black holes in neutron stars. The one thing about black hole mergers, though, is that there's no matter involved. Because there's no matter, there's no electromagnetic emission. And we just have the gravitational waves, and that's it. Neutron star mergers, on the other hand, as you can see, are very messy because the matter that formed the neutron star then is redistributed around the gravitational potential, or the metric, if you want to speak in GR language. And when you have a merger, typically what happens is that most of the mass that was in the binary goes to the central object, and then some mass is ejected promptly on an orbital time by tidal interactions or the collision between the 2 stars. We call that dynamical ejecta because of the dynamical time. And then there's some matter that is not unbound, yet has angular momentum, and so it circularizes into an accretion disk around the central object. It's accretion disk. And of course, an open question is when do jets or relativistic jets emerge from these systems, such that we can see a gamma ray burst. It's a technical question. The current view is that it is a lot easier to have a jet coming out if you have a black hole neutron star merger, because all this region above and below the central object is not populated by matter. Whereas when you have a double neutron star, you have matter everywhere, and so it's harder to accelerate matter to relativistic speeds when you have a lot of mass. So this is an active, very active area of research, and there's lots of groups doing numerical relativity working on this problem. So this diagram, schematic, illustrates how different phases of the merger relate to different counterparts. Phases we call inspiral. That's when the neutron stars are approaching each other, and that's where most of the signal that LIGO sees comes from, just because their sensitivity range is hundreds of hertz. So that's where most of the signal comes. Then we have the dynamical phase when we have this coalescence. And right after we have this accretion disk forming, and so it's accretion phase, where mass is ejected and possibly you can have a relativistic jet coming out. When you have a neutron star as a central object, this can happen if the total mass of the binary is not high enough to make a black hole immediately. And then you can also have post-merger gravitational waves from the neutron star remnant. Okay? Those, however, are a kilohertz frequencies, and so LIGO cannot see them unless they're really close, so we have not yet seen them. In parallel, we have short gamma ray bursts, and then at later times, once the blast wave from this ejecta propagates out, we get the kilonova transient that can shine in multiple wave bands, and even in the radio when the blast wave collides with the interstellar medium. Importantly, there are nuclear processes taking place in this merger, and we here R process. The R process is really one of the 2 processes that generates the elements heavier than iron, or zinc more precisely, that involves neutron capture on seed nuclei. And neutron capture is easier than charged particle capture because of the Coulomb barrier. And the R process in particular is characterized by the neutron capture rate being higher than the beta decay rate. So when you add a bunch of neutrons to a nucleus, it becomes unstable, and so the neutrons start decaying into protons instead of the beta decay phase. That eventually leads to what the nuclear physicists call the value of stability. This is a neutron number, proton numbers, and nuclear chart. And so our process goes generally at the neutron-rich edge of this nuclear chart, and then by beta decay, we reach the value of stability at the center. And so traditionally, but nuclear physicists had known about this for a while because this is the only practical way to make the heavy elements. But what was not clear is where in nature did this process happen. Okay? The candidate sites were neutron star mergers and core-collapse supernova, but not until GW17 and 17 did we have evidence for this process taking place in neutron star mergers. And that evidence was in the form of a kilonova. And just to quickly review how do we produce electromagnetic radiation, in this event, we have a blast wave that's expanding that eventually becomes transparent to radiation, and this time to transparency, the time to peak, depends on the opacity of the material, the mass of the ejecta, it sets the diffusion time, and then the expansion velocity. Okay? And this transient essentially shows a peak, and then thereafter it can continue to shine as long as there is a persistent energy source. And in particular here, we're talking about radioactive heating. So our process heating, or in the case of type 1a supernova, we have a nickel 56 decay. And then the light curve of this transient follows the radioactive heating right after the peak that you see initially. So the opacity happens to be important here because our process elements have more complex atomic structure than lighter elements. So basically, for optical photons, there are many more ways of being absorbed. And so what that means is that if you have even a small amount, like 10 to the minus 3, 10 to the minus 2 mass fraction of our process elements in your ejecta, the signal that comes out shifts from the blue optical, which is what you get in normal supernova when you have ion-dominated opacities, it shifts to the infrared. Just because the diffusion time is so much longer. So the transient is dimmer, lasts longer, and then it shifts to the infrared. And this is really the evidence we have for our process elements being generated in GW17 and 17. This is spectral energy distribution as a function of time from one of the groups that followed up this source. And the specific sequence of changes in color and luminosity can only be accounted for with a kilonova transient. So that's the importance of understanding, how kilonovae are generated. Any questions thus far about this?
Yeah, I have a question. So I'm not very expert in this experiment. By means of mass ejecta, do you mean the bipolar outflows or something else?
Yeah. So maybe here. If you notice, there's matter being ejected on the dynamical time. This will move out, and then the accretion. This will also eject mass later, and that's what I'm going to talk about later. Okay. So that those two ejecta components contribute to this blast wave that eventually generates the kilonova transient. And the opacity is important because it sets the time scale and the color of the transient. And that's what really gives you the evidence for our process element presence. Okay, so now I'm going to talk about disk outflows, which is what I work on. And okay, we're in this grand scheme of things, we're talking about of course, these arrows that we have on top of the accretion disk here. So it's an outflow from the disk itself. So just to review a bit of disk physics, an accretion disk is formed by gas orbiting a central object. Gravity is mostly balanced by the centrifugal acceleration. So things are rotating, so they cannot spiral in. It is gas, right? So there's thermal pressure that provides partial support, and the amount of thermal energy compared to, say, the gravitational energy determines how puffy the accretion disk is. So very little thermal energy is almost equivalent to having, the asteroid belt, right? So it's really thin, a cold disk. But if the disk is very hot, then there's more extended vertical structure because there's more random motion of the particles. Hence the puffiness or the scale height of the disk is set by the thermal pressure component. And if you want accretion to occur, we need to have angular momentum being removed from the inner regions of the disk. And also we need cooling so that matter can settle into the central object, otherwise it just forms an atmosphere, hot atmosphere above it. And so in neutron submerged disks, angular momentum transfer is thought to occur by the magnetorotational instability in the same way as, say, AGN disks or X-ray binary disks, because it's fully ionized. And the cooling channel here is neutrinos. The optical depth to photons is something like 10 to the 20. Okay, so it's extremely super Eddington. And so photons are just a trapped gas into matter. And so neutrinos really are the cooling agent that allow matter to settle into the central object. Now, mass can be unbound from the disk because by a variety of mechanisms, but the main mechanism has to do with the fact that this neutrino cooling channel is not persistent, but it goes away after a little time. So the disk accretes, decreases in density, and so the neutrino emission drops. And so then we have viscous heating or dissipation of MRI turbulence heating the disk, but there's no more cooling, and so there's thermal mass ejection arising from the disk. And also, there's if you include the MHD effects, you have the Lorentz force that can eject matter mechanically. And then there's also nuclear processes such as the recombination of nucleus into alpha particles that release energy and also contributes to this thermal outflow at late temps.
So what's the time scale on which neutrino cooling matters?
It's the viscous time. It's roughly 100 milliseconds, 200 milliseconds.
200 milliseconds.
Yes.
And then it becomes optically thin neutrinos.
Yes. So the neutrino emission just drops.
Because
It becomes becomes a relatively inefficient disk, like an AF. So it just blows up. So the questions we want to ask here are what is the outflow mass and the properties of this outflow? What is the contribution to the R process? So what's the composition of this outflow? And then how does it translate into a kilonova signature? Okay, so if there's a jet and so on, what's the electromagnetic signature we get from this outflow? Okay. And so just for reference, this is an animation of one of the simulations that I have performed on this problem. For 10 years now, we have been able to produce time-dependent models of this problem. These are the simulations I'm showing are axisymmetric, two-dimensional simulations, and so this is the top panel shows the central object, and a zoom in on the inner disk, and you see that there's mass ejection from the disk, which is this thermal outflow you get once the neutrino cooling shuts down. And in terms of amounts, usually 10 to 20% of the initial disk mass is ejected. The material is neutron rich. The electron fraction YE, which is a measure of the ratio of neutrons to protons, is low, which means that there are more neutrons to protons than protons, and then that means that you will make our process elements. These are hydrodynamic simulations with shear viscosity, which means that the outflow is only thermal, right? There's no MHD effects here. And so for these viscous hydro simulations, the outflow speed is about 0.05 C, 5% of the speed of light, which is a factor of a few lower than the dynamical ejecta, which is 0.1 to 0.3. And by now, there are several groups that have worked on this problem by now, doing viscous hydrodynamic simulations. Of course, the fraction of the disk ejected depends on various things, in particular, the mass of the disk and the distance of the disk from the black hole. And one way of showing that is using a parameter which we can call the disk compactness, which is the ratio of the disk mass to the black hole mass to the distance between the black hole and where most of the mass of the disk is. So basically, how strong is the gravity at the position where most of the mass is. And then if one does a parameter study, one finds that the fraction of the disk ejected, so that's the mass ejected over the initial disk mass, is a monotonically decreasing function of the compactness of the disk. So the more compact, not surprising, the harder it is to unbound mass because the gravity is strong. Right? This is kind of a clean way to show that the fraction of mass ejected is not a fixed number, but it actually has parameter dependencies. One can also look at the composition of the disk, and the way this is usually done is one places tracer particles on the disk, and these are passive tracers that follow the disk evolution, and then one post-processes that with a large nuclear network. The reason one does that is because these hydrodynamic simulations have a finite amount of memory. So for each isotope you want to include, you need a full, grid quantity. Right? So if you think about 7,000 isotopes, that's impossible to have in a time-dependent simulation. So one follows a few species and then does the tracer particles and then uses the tracers on this nuclear network. The question is it subconsistent? And the answer is, as long as the radioactive heating is not too important, which it is not at early phases, then it will not affect the dynamics. So the detailed composition is not going to be dependent on the actual radioactive heating. And this is a project we did with Meng Wu from the Institute of Physics back in 2016. So the results of this composition usually look like this. This is a plot showing mass number of elements versus the abundance at 1 gigayear. So you run the network until significant number of nuclei have undergone full beta decay to stability. And then the dots on each plot are the solar process abundance, and the color curves are results one obtains from different disk realizations. On the left, we have disks that vary the viscosity parameter. So the alpha viscosity in this case for viscous hydro simulations. And on the right, we have two disks that have identical parameters except the disk mass. Right? And you notice that at the light end, so we're talking, A mass number of 80 to about 130, so it's the second R process peak, things do not vary that much. But then the heaviest R process elements, second to third peak, here we're talking about gold and lead and all those very heavy elements, is very sensitive to the details of the disk dynamics. Right? Very robust, light R process contribution, very variable, heavy R process contribution.
Is it a semi-analytical work? I mean, if fully numerical, one does not have to assume the value of alpha viscosity. So,
if you do GRMHD, then you don't.
no, even if non-GR, a full numerical simulation does not have to assume particular value of alpha viscosity. For semi-analytical works, yes, they must introduce.
Yeah, you do need alpha, otherwise you don't have accretion. So you need to put a viscous stress tensor and then specify the viscosity.
Yes, and such turbulence automatically incurred in the simulation.
Mm-hmm.
So I think explicit value of alpha does not have to be introduced for full numerical simulation.
If you believe the viscosity that goes in is fully physical, yes, but I think nobody has come up with a viscosity prescription that captures GRMHD reliably, as far as I know. The alpha parametrization is one way of parameterizing it, and you can calibrate it. So I compare hydro with GRMHD, and it's between 0.01 and 0.1.
Well, I have more comments, but let's discuss later.
Sure, yeah, we can discuss.
Thank you.
Okay, so another aspect that affects this dynamics is whether the central object is a neutron star or a black hole. And the reason is that when you have a remnant neutron star, you have a hard surface, so you don't lose matter to the black hole. And then you have significantly more neutrino emission which means more neutrino heating, which then means that more mass is ejected relative to the black hole case. And then the composition of the outflow, we have here the electron fraction. Basically, blue is very neutron rich, and 0.5 is equal numbers of neutrons and protons. The composition is very different because of the significant neutrino emission. And the reason, of course, is that neutrinos can change neutrons to protons and vice versa through weak interactions. And so generally, when you have more neutrino heating, you essentially raise the entropy, heat up the material, and that essentially means that you have more positrons, and then the equilibrium value of the neutrons and protons tends to be towards equal. In the limit of very hot material, it is exactly 0.5, but once you start introducing degeneracy and suppressing the positron abundance, then you get neutron-rich outflows. Okay, so that's essentially the reason why we have these different compositions. And so then, if one does the same tracer particle study and gets the composition, one also finds that the lifetime of this remnant neutron star also modifies the composition. All these curves here represent remnant neutron stars that lived for different amounts of time and collapsed to a black hole after 10 milliseconds, 30 milliseconds, 100 milliseconds, or 300 milliseconds. Okay. So these are the dependencies of this flow. A student and I tried to match the mass and velocity of GW17817, and this mass and velocity were inferred from the kilonova light curve. So you can fit a light curve and then obtain the mass and the velocity as parameters, right? So the top panels show a blue and a red band, which are the observational constraints on the ejecta mass, and the bottom panels have a thick blue and a red band, which are the constraints on the velocity of the outflow. And the dotted line is something else. But the important point here is that from the simulations, one can compare the mass ejected and the velocity. And we showed that with viscous hydrodynamics, we can reproduce the mass. This is the top panels here. We can come close to the mass ejected. Blue and red means blue kilonova, red kilonova, poor and rich in very heavy elements. That's the opacity effect. However, the velocity is very difficult to match when one uses viscous hydrodynamics. That's because it's thermal mass ejection. And so that motivates using MHD, in particular GR MHD, because we have a compact object. And so we did GR MHD simulations of these problems a while back to compare with viscous hydro and see how much mass was ejected. And these are the details of the simulation, but basically it's a standard black hole accretion disk that has neutrino cooling and nuclear physics, which are the distinctive ingredients of neutron star merger disks. And the important result, this is the outflow rate at a large radius, and then this is the time. What you see in the color curves is the mass ejection at large radius from viscous hydrodynamic simulations with different values of alpha viscosity. And the black curve is what you get with the GR MHD simulation, in which you do not have to specify any value of alpha or the viscosity. It's just self-consistent from the MRI turbulence coming up. And in that case, we have a factor of 2 more mass ejected when we do GR MHD compared to viscous hydro. And not only that, we get higher velocities. Okay. This table shows a comparison between 3 GR MHD models that vary the magnetic field strengths and topology. So BT is toroidal, BPW is weak poloidal, and BPS is strong poloidal. And then the lower 3 rows show viscous hydro with 3 values of alpha. And this column here with the percentage shows the percentage of the disk mass that was ejected. And as you can see, there's a monotonic relation between the strengths of the viscosity, which we knew, and also the magnetic field strength and geometry. So the stronger the initial poloidal field is, the more mass is ejected. And also the outflow velocity is significantly higher when you have a strong poloidal field compared to what you get with viscous hydro or even a toroidal field. It's very slow. A student of mine, Stephen Fallman, has been modifying Flash to solve this problem, adapting the grid and adding the neutrino physics and the nuclear physics and the equation of state to be able to model this in a computationally more inexpensive way than doing geometry simulations. The reason is that the disk outflow is produced at large radii compared to the horizon of the black hole, and so GR effects are not that important in setting the mass ejection from the disk. So you can do pseudo-Newtonian physics. If you want a jet, then no, of course you have to do GR/d because otherwise it's just a jet does not come out. But if you just care about the mass ejection, you can get away with pseudo-Newtonian dynamics. And this is just a histogram of the 3 simulations he carried out showing composition, electron fraction, outflow velocity, in units of the speed of light, and then the angular dependence of this mass ejection. And we have results that are consistent with what we get a GR/MHD. More mass ejected when you have a strong colloidal field, less mass ejected when you have a more compact accretion disk. And then the toroidal field also ejected mass, but the speed is lower than when you get a strong colloidal field. This is a bit of a sidetrack project, but it's more speculative. So GW17 showed non-thermal emission due to essentially the jet, the afterglow of the GRB, which was a power law in time. That had the same spectral slope between the X-rays and the radio for a long time. And then observations were made at 3 years post-merger, and it was claimed that the X-rays deviated from the predicted power law of the afterglow, and there was an excess X-ray emission. The observers are not fully in agreement because there's another group that says no, it's an instrumental effect, and there's no statistically insignificant excess. But nevertheless, theories produce models to try to account for this X-ray excess. So Brian Metzger and I tried to see if we could make it happen with accretion. Right? So what you see here is the accretion rate on one standard accretion disk that has the parameters of GW17 or 17 as a function of time from 10 milliseconds to 10 years. Okay. 10 to the 8. No, it's not 10 years, it's 3 years, not 10 years. And then this is the X-ray excess. And what you see here is the accretion rate. Initially, there's neutrino cooling, but eventually there's an accretion rate below which there's no cooling anymore. Yet the Eddington limit is way down here. There's also no photon cooling. And so the disk is relatively inefficient, and there are no energy processes taking place. Once it cools down, there's no nuclear physics taking place. So one can extrapolate the accretion rate in this pretty much self-similar phase, and basically just ask a plausibility question: could we possibly explain this X-ray excess? And the answer is, in principle, yes, if things go correctly. Just extrapolating this accretion rate, it kind of lands in the right spot if the viscosity is one particular value. If you change it, you don't quite land in the same spot, but it is in principle possible. Now, of course, it's very speculative, and as I said, the observers don't even agree on whether there's an X-ray excess or not. The problem is that it's very faint. It's been 3 years or more, like 6 years now. And so I don't know if there's going to be ever another data point. Okay, so in the last few minutes, I'm going to talk about the effect of the neutrino flavor transformation. So traditionally, when people include neutrinos in the simulations, both neutron mergers and core collapse supernova, one essentially does classical transform, which means that one solves the Boltzmann equation, classic Boltzmann equation, in some approximate way. For example, taking moments, the usual M1 method, which is the zeroth or the first moments of the Boltzmann equation or relative transfer equation, if you wish, right? Or leakage scheme or flux limited diffusion or any other approximation to the Boltzmann equation is an approximation to the classical Boltzmann equation. Okay? But it turns out that neutrinos are quantum particles and they can change flavor. Okay, so the real equation that governs their evolution is the quantum kinetic equation. This is a distribution function matrix that has on the diagonal the actual densities, and on the off diagonal has the quantum coupling between the wave functions. And this is really the Schrodinger equation. It depends on the Hamiltonian and the collision term of the neutrinos. And so the Hamiltonian in particular has a component due to vacuum flavor transformation, and this is because the mass eigenstates of neutrinos are not the same as the flavor eigenstates, and so you can have vacuum oscillations of neutrinos propagating, and this happens in the sun. The matter component is the MSW effect, and also there's a resonance between the electron neutrinos and the electron density. And then this new term is very complex, is the neutrino-neutrino interaction. And it's relevant because there are so many neutrinos in this problem that the probability of scattering or collision between neutrinos is significant. And that can generate complex effects in the evolution, particularly the flavor evolution. So a few years ago, people showed that there's an instability due to this Hamiltonian component that essentially very quickly on nanoseconds and centimeter scales sets in and changes the flavors of neutrinos. Thus far, what they find when they do these little box simulations is that you tend to reach some kind of stationary state in which you can approximate the system as being in rough equipartition between the flavors of neutrinos. Okay. Meng Ru work on this at the Institute of Physics. So, and most of the simulations are quantum kinetic simulations, which are very expensive. So they can only be done on a little patch of the disk or the supernovas, the local simulation. What we try to do with Sherbert Reichers and other collaborators is to come up with a global prescription to include some of the important effects of this fast flavor instability into a global viscous hydro simulation. And so what we do is simply take linear combinations of the luminosities and the neutrino energies in a way that we can tune whether there's real equipartition between the flavors or some other, for example, lepton-conserving equilibration, and essentially see what happens. What's the effect on the mass ejection, on the composition of messing up with the neutrino flavors on a global large scale. Okay? And so this is the activation parameter, basically where in the disk the instability sets in, and basically this depends on the optical depth, because this instability only takes place where neutrinos are out of thermal equilibrium. So essentially there needs to be an asymmetry between neutrinos of one flavor moving in one direction and neutrinos of another flavor moving in a different direction. Okay? If they're in thermal equilibrium, they're all moving like isotropically. And so this is the end result for the composition. The gray histograms are what happens when you don't have any flavor transformation. And then the color curves are different strengths of flavor equilibration. 2/3 means that all the flavors have equal numbers of neutrinos, number densities, and 1 is a full swap of heavy lepton neutrinos to electron neutrinos. And the net effect is to move the peak of this histogram to the left. And if you see the x-axis is YE, that's electron fraction. So it's the asymmetry between neutrons and protons. Essentially, the outflow becomes slightly more neutron rich, okay, compared to what happens when we don't have any flavor transformation. When you have a neutron star remnant at the center, you also have a protonization of the outflow. So you have more proton-rich as well as more neutron-rich outflows. The distribution broadens, and that's because not only the numbers of neutrinos are being swapped, but also the energies. And so the relative driving, so the absorption of neutrinos becomes more important. So you have a stronger neutrino-driven wind coming out of this. Okay, and this is a more technical plot that shows you why we know that the relative driving is important. Okay? And these are the trends in mass ejection and electron fraction, composition, and velocity. So the black curve is pure black hole. The purple curve is a short-lived neutron star. Blue and red are longer-lived neutron stars. And so for black holes and short-lived neutron stars, we get very limited effects. Some neutronization and some very small change in the speed. And for neutron stars that live longer, then we have more proton-rich composition and significantly more velocity. That's because there's more relative driving that that pushes the outflow a bit faster by neutrinos. So, okay, and this is the nucleosynthesis effect. It's the important plot because we want to know how much this flavor transformation changes the mass fraction of the elements that change the opacity of the transient, and the answer is that it's very little. Okay, the mass fraction of these lanthanides, the elements that influence the opacity, is at most a factor of 2. So it is not a drastic effect on the electromagnetic counterpart, nor on the composition. And so thus far, with this study, we assess that this flavor transformation is not going to significantly alter our previous predictions for this outflow. And the future directions, of course, we want to do more MHD simulations. These are expensive because they have to be done in 3D, right? Ideally, one has a more efficient method to do them. For instance, pseudo-Newtonian simulations in MHD, or more efficient GRMHD codes. Also get the dynamics of the jet and the short GRB. Many people are working on having more realistic initial conditions for this disk outflows. So traditionally, people just start from an equilibrium accretion disk, as is done in AGN simulations and extra binary simulations. Just have an equilibrium torus and then you let it evolve. But mapping matter from a merger simulation that solves the Einstein equations to a simulation that just has a fixed metric, that's the one used for the accretion disk, improves the initial conditions and then gives a more reliable, for instance, initial magnetic field geometry and strength than just imposing it by hand. Okay. Ultimately, what we want is end-to-end modeling that, unfortunately, given the different regimes, we have to use different codes for different phases of this transient, but passing the output of one code to another, and so on and so forth, is the ideal way to kind of have something self-consistent to make more reliable predictions. That's the end goal. And yeah, so I'm going to leave my summary there, and thank you very much.
Any questions or comments?
Thank you. I'm not sure. First of all, I know very little about any of this, but at the end of the day, can one actually compare these production rates of our process element abundances to measurements in either stars or on Earth? I mean, is there quantitative templates against which this can be measured? Have we solved all our questions, or is there still questions remaining?
Yes. So people, in fact, and we, in one of our papers, compare the abundances with the metal poor stars in the halo of the galaxy, because people can measure the abundances of some R process elements that have strong transition, so they see strong lines, right? So they need to do high resolution spectroscopy of these metal poor stars in the halo. And yeah, there's plenty of data that one can compare with. And generally, the conclusion is that the heavier process element abundance is very robust. It's very similar to the solar R process abundance, but the light R process, like mass number, 80 to 130, is very stochastic or varying. And yes, it just so happens that we know how to make this heavier process element. This is called fission cycles, and the fact that it is very fluctuating on the the light R process side. I don't think anybody has found an answer, but we have shown that you can have it through multiple channels, such as the disk outflow or disk collapsers that people are looking at now for production of a LiDAR process.
Okay, let me see if I understood. So, is now the situation that all R process element production can be explained with just this one mechanism?
Oh, I see. Yeah. Okay, so you're talking about production. No, actually, I think there's an issue with neutron star merger, which is the delay time. Right? So if you see metal poor stars very early on in the life of the galaxy that have our process elements, it's a problem for relying only on neutron star mergers because there's this time delay, like you have to have in spiral of the neutron stars so that gravitational waves can kick in. There's a bottleneck there. There's 100 million years or so. And so that's why people have proposed things like collapsars or supernova to explain at least some of the early.
But it's only the metal poor stars that may have an issue. And
Yes.
of course, that needs to be model dependent. I think
Yes.
it depends on your IMF of the first generation. Of stars.
Absolutely, yeah.
But otherwise, let's say on Earth,
Mhm.
there's no more, like all the Earth's processes can be explained this way.
I think so. Yeah, so I mean, one can play around with, so I show you the disk outflow abundance here. And you see that the heavier process element yield is very low, right? But then the dynamical ejecta, the one that leaves very quickly the system, it's very neutron rich because the neutrinos don't have time to change the composition, and it gives you almost exactly this heavier process composition. So if you add the two, you usually fit the solar abundance pretty well. So yeah, there's no problem in producing the solar process with the disk and the dynamical ejecta.
The disk and
The dynamical ejecta.
the
Dynamical ejecta. So
dynamic ejecta.
the prompt outflow. So it's really, as you say, it's the metal poor stars that are very early on that people say, oh, but the time delay, but it's not. It's a controversial. If you ask the observers that do this, no, they don't agree, right? So it's not settled.
Well, and model dependent. It depends on how early what the first stars were.
So if you compare the outflow properties like mass loss rate and outflow energetics from neutron star to black hole and other stellar object like photostar or Hyman star, there should be some difference in the due to their driving force and mass difference in the driving force, right? Can you comment on that? What is the difference between the energetics of different type of objects?
You mean the driving mechanism of the outflow, or?
Yes, like that. I would like to know the outflow energetic or mass loss rate. What is the difference in between different objects? What is the scale factor?
Oh, yeah. Here you have mass ejection that is measured in solar masses per second. Right? So, right, solar masses per second.
Yes, yes.
So stars are solar masses per year and like 10 to the minus 8, 10 to the minus 9. The most, the strongest winds are 10 to the minus 5 solar masses per year, right?
Yeah.
So this is solar masses per second.
Right.
So it's 3 times 10 to the 7 times, at least bigger, 10 to the 12 times bigger.
Thank you. And another, in one plot, you plotted accretion rate versus time.
Mhm.
So there, you showed that within 10 years, like that rate will decrease to 10 to the minus 15 or something.
This one?
So yeah, that plot.
Mhm.
That means whole accretion should the main accretion should occur within 10 years of only. That is that mean this plot like.
Well, what happens is that what this means is that the disk transitions from neutrino cooled to basically relatively inefficient, nothing can cool it, to photon cooled once it reaches this line here. And once it reaches this line, it becomes an X-ray binary disk, right? And so you have this classic accretion disk phenomenology of super Eddington accretion or sub Eddington accretion to black holes, right? Where photons are actually carrying the energy because they're now optically thin. Right? So that's why one can plausibly explain that data point with accretion.
Okay.
Do you expect composition difference between kilonovae and supernovae?
Yes. So this Yeah, so this in supernova, for the most part, the ejecta is made up of some iron group elements, but also the inner layers of the star, like carbon, oxygen, magnesium, and so on. Right? And how much our process elements are produced is really an open question yet. People find that there's some our process production, but very little, right? Very little, and not reaching the heaviest our process elements. Whereas in neutron star mergers, essentially all the ejecta is our process.
Thank you. My question on accretion disk may be too detailed and may not be interested in by the audience. That's a central part of the talk.
Yeah, question.
Yep.
I'm interested in the mass of nickel 56, and as I remember, you may mentioned about the kilonova light curve at the very late phase, nickel 56.
Oh, no, I said, yeah, maybe I misspoke. What I meant is that type 1a supernova, they have nickel 56 that dominates the time dependence of the light curve. It's like the half-life of nickel 56 and then cobalt 56. In kilonova is our process elements, so it's not one species, it's a power law. Okay, there's many half-lives combined.
Okay, so yeah, do you think any disk outflow inside? How much nickel can be ejected?
How much nickel? It depends on how much matter with how much matter with electron fraction of 0.5 you make. Right? Here we don't make much.
Yeah.
Here we have not much either from the black hole accretion disk. Here you maybe make a bit more, but with the flavor transformation in the neutrino, right? And the reason is that nickel 56 has equal number of neutrons and protons, so you need to have YE of 0.5 to make nickel.
Mhm.
Any questions?
So in your simulation, I mean, is there any significant contribution from the changing of magnetic field? I mean,
Changing of magnetic field?
yes, where neutron star merge happened.
Oh, yes. Yeah, it's a good question. So one of the open questions right now, only one group in the world actually has achieved it, is what is the initial field distribution in the disk, right? To answer that question, one needs to run a GRMHD merger simulation, right? And then map into a fixed metric code with the field that came from the merger simulation, right? And what we did here is just use a fixed metric code, but just impose the magnetic field. And what those simulations show is that the field is very turbulent initially. And there's no large scale poloidal field and so on. A toroidal field develops because of the rotation, and it starts winding and growing. But initially, like right after the merger, is stochastic and turbulent.
I wonder if dynamo effect works for the accreting phase. Well, if one performs in GRMHD simulations, then I wonder if they find dynamo effects, amplification of magnetic field.
Yes. Yeah, so the MRI amplifies the field by turbulence, and then there's winding. So you have this vertical jet.
Yes. So I wonder if such dynamic amplified magnetic field could significantly change the argument.
Yeah, absolutely. And it's also the people who do these GRMHD merger simulations, they cannot fully resolve the magnetic instabilities. There's Kelvin-Helmholtz instability at the interfaces of the stars. There's very small scale, and they cannot. So they increase the resolution and they have a higher field, they increase more, so they have not converged yet. So
Yeah,
That's an open.
it's 3D dimensional, yes, it's
Yeah.
always a problem.
Yes, that's very expensive.
Any questions or comments?